Hi there. In this video, we'll be talking all about error. And basically, when we're talking about error, we need to talk first about accuracy. When we're talking about accuracy, we're saying, how close is our measured value from the actual value? For example, if we've measured temperature, and we've got a temperature measurement of 24.3 degrees, for example. What's our actual temperature? Maybe it's 24 degrees. And that difference between the actual and the measured is our error. And so our error, we say measured value minus actual value, or if we think about our measurement as a system, as a complete system, what's the output of the system minus the input of the system in terms of the output as a certain measurement in temperature or volts or g-forces or whatever it is, minus the input of the system in terms of whatever unit that is. Now, of course, it's desirable that our error be as small as possible. And we'll talk about where those sources of error come from, what causes the error. But also it's important to note that our error can come along when we're actually performing the measurement as a result of performing that measurement. It can come along during our processing of that data. It can also come into our sensor measurement as we actually send that data or transmit that data, communicate it somehow to a computer or the internet or whatever it may be. So there's multiple sources of where that error can be attained. We should say though that it's important to differentiate between two types of error, our systematic error and our random or non-systematic error. So with our systematic error, we're basically looking at errors where we've got something that's an offset or a scaled factor above what we're expecting. So everything might be higher by 0.1 of a volt, or everything might be higher by 0.1 of a volt and then offset by a different sensitivity factor. So all those things are possible. And typically we can use some calibration and characterizing that sensor to remove some of this non-systematic error. Our random errors are a bit trickier. It's where we've got some measurements might be higher, some measurements might be lower, and we can't really predict them. Some of these errors might be caused by noise, for example, or an operator being careless and kind of not performing readings particularly well, or writing numbers down in reverse order, or all sorts of things could be going wrong there with our random errors. Let's talk about some of those sources of error. So some of those sources of error, particularly when we're thinking not just about the operator reading things, but also in the actual measurement itself, is actually measuring the error we introduce when we're actually performing a measurement. So some of our sensors are what we call self-heating, which means as we perform our measurement, the sensor warms up over time, which will of course disturb the operating environment we're operating within. Or maybe even a more intuitive example, if we've got a cup of water that we're boiling or warming up slowly, and we dip a thermometer in there, that thermometer is going to be at a different temperature to the water that we were heating up. And so we're actually going to probably cool that water down as it's starting to get hotter by entering the thermometer. And then if we pull the thermometer out and we put it in again 5 minutes later, we're actually going to be introducing an error into our system as we're trying to measure what the temperature actually is. Another one is just when we're reading analog values with our human eyes, we get this parallax effect where we see like an analog sensor, the one above. Depending on how we look at that analog sensor, what angle we're looking at it from, we'll actually see a different value. I remember when I was learning to drive and my parents were supervising me in the car, there'd be the odd occasion where they'd say, "Oh, you're speeding, slow down." And I'd look and I'm actually doing exactly the right speed because I'm looking straight on at that sensor. But when they're reading from an angle, it's maybe added 5 kilometers per hour to whatever measurement was being displayed by the speedo. And so with our analog values, it's important to actually do that, to actually read with the right orientation towards it. It's also a reason why digital's quite handy because we've got a series of numbers, not something that's subject to parallax errors that we can have here. Electrical noise, which we'll talk about in a following video, and how this can introduce errors into our measurements. Our system might be poorly calibrated or not calibrated at all. And that poor calibration or characterization of our sensors can introduce all sorts of errors into our system. Now, our system might be damaged or broken in some way. Maybe we've subjected it to too high voltage or pressures or accelerations or temperatures, whatever it may be. We may have damaged our sensor or part of our sensing module there. We might be measuring our sensor at the incorrect rate. We talked about aliasing before with our analog digital converters. We need to sample at an adequate rate to reproduce our signal in digital domain. And we might have some sensors that we have error that accumulates over time. For example, if we're developing an inertial measurement unit that we use sometimes for navigation with gyroscopes and accelerometers and things, we can have an error that accumulates over time as we integrate that data because, well, we measure how much we've accelerated or decelerated, and we just keep on measuring those values and we keep on adding them together, and each of those will have an associated error with it. When we add all those ones together, our possible error size or area of uncertainty keeps on increasing and increasing.